In this video, we're going to dive a little bit deeper into enthalpy and look at exothermic and endothermic reactions and a little bit deeper. So exothermic reactions, like we said in the last video, heat is leaving us, so the temperature of our surroundings increase. And for reactions, that comes from two chemicals reacting, and the potential energy of those chemicals and the products form is lower than their reactants form. So since the energy is lower and we have the law of conservation of energy, that energy has to go somewhere, and it goes into heat that is absorbed by our surroundings. So for this type of reaction, we break old bonds and form new ones. Products have less chemical energy than the reactants, and we release heat, like I just said. Endothermic reaction is the opposite, where we need, for our reaction to happen, we need to absorb heat. We absorb it from the surroundings, so the temperature of our surroundings go down. In this case, our products have more potential energy than our reactants. And to get this internal energy, we need to get it from somewhere. Law of conservation of energy. So we get it from our surroundings. And let's now think of the enthalpy of reaction. So enthalpy is a extensive property. Extensive property means it depends on the amount of stuff. We covered this all the way back at the beginning of the semester, what extensive and intensive means. But basically, the more stuff you have, it's going to have a bigger effect. So for enthalpy, the more gas you have, the bigger the fire. And we can calculate enthalpy change for moles of reactants. So for example, let's look at this where we have C3H8 plus oxygen goes to CO2 plus H2O. We're burning butane. And the change in our reactants is minus 2044. That's why delta H is negative. And that's what I mean that you write in moles of reactants. So 1 mole of C3H8 is negative 2044, or 5 moles of oxygen is negative 2044. This whole reaction is negative 2044. So let's think about this. Let's give you some practical experience. Nitromethane burns in the air and we get a lot of heat. Delta H reaction is minus 1418 kilojoules. So if we have 5.56 kilograms of nitromethane, how much heat do we produce? Alright, see if you can figure that out. So let's take a look at this. So delta H reaction for 1 mole of nitromethane is minus 709 kilojoules. Okay. So 5.56 kilograms of CH3NO2. 1 kilogram of CH3NO2 is 1,000 grams. And the molecular mass is 61.04 grams of CH3NO2. That's 1 mole of CH3NO2. 1 mole is minus 709 kilojoules. So that's why I have the delta H reaction here in kilojoules per mole. When I gave you it in the 1418, that was for 2 moles of nitromethane. But I want to work in 1 mole of nitromethane because that is now a conversion factor. I can go from mole to kilojoules. If I just use the 1418 and I get to this step, well, I'm stuck now because I can't go to kilojoules. So multiplying everything and dividing, I get with this much nitromethane, the amount of heat I release is 6.46 times 10 to the 4 kilojoules. That's it for this video. I'll see you in the next one.